In the quantum realm, particles can exist in multiple states simultaneously. Think of it as overlapping waves. This is best exemplified by Schrödinger's cat, both dead and alive until you peek inside the box. Imagine traditional computer bits replaced with qubits, which can be in a superposition of states, just like Schrödinger's cat. This opens up a world of possibilities, but it also brings challenges. That's where the concept of squeezing comes in. A recent paper from researchers Ranjit Singh and Alexander E. Teretinkov shows how we can boost quantum text sensitivity using squeezed Schrödinger cat states. But what does squeezing mean? Essentially, it's about reducing noise, those pesky random signals that mess up measurements. By squeezing these cat states, we can cut down the noise and amplify the useful signals. This means more precise measurements and more robust quantum technologies. Singh and Teretinkov discovered an optical parametric process that increases the number of photons in these states while preserving their interference properties. In simpler terms, it makes the system more sensitive and accurate. Why is this important? Well, reducing noise and enhancing sensitivity is crucial for the advancement of quantum sensors and other technologies. Imagine detecting the tiniest changes in a system with unprecedented accuracy. That's the power of squeezed Schrödinger cat states. This research is not just theoretical, it has real-world implications. Quantum sensors using this technique could revolutionize fields from medical imaging to navigation systems and beyond. Let's delve into the concept of quantum squeezing itself. Quantum squeezing is a fascinating technique in quantum mechanics that allows us to reduce the uncertainty or noise in one property of a quantum system at the expense of increasing the uncertainty in another. This principle is rooted in the Heisenberg uncertainty principle, which tells us that certain pairs of properties like position and momentum cannot both be precisely measured simultaneously. In more technical terms, quantum squeezing usually refers to manipulating the quantum states of light, such as photons. By squeezing the quantum state, scientists can reduce the noise in one variable, like the amplitude of a light wave, while increasing the noise in the conjugate variable, like the phase of the light wave. This process allows us to make measurements with a precision that surpasses the standard quantum limit. So, how is quantum squeezing achieved? There are several sophisticated techniques. One popular method is optical parametric amplification, which uses a nonlinear crystal to convert a high-energy photon into two lower-energy photons. By controlling these photons carefully, scientists can reduce noise in one quadrature while increasing it in the conjugate quadrature. Another technique is four-wave mixing, which involves a non-linear medium where photons from a pump beam interact with photons from a probe beam to generate squeezed states. This method is often used in atomic vapors and optical fibers. Then we have electromechanical systems where mechanical oscillators are coupled to electromagnetic fields. By cooling the mechanical oscillator to its ground state and driving it at a specific frequency, squeezing can be achieved. This is particularly useful for creating squeezed states in the microwave and optical domains. Josephson parametric amplifiers, or JPAs, are superconducting devices used in quantum computing. They exploit the non-linear inductance of Josephson junctions to produce squeezed microwave states, enhancing the sensitivity of quantum measurements in superconducting qubits. Finally, cavity optomechanics involves coupling a mechanical resonator to an optical cavity. By driving the system with a laser at a specific frequency, mechanical motion can be squeezed, reducing noise in one quadrature. However, achieving quantum squeezing is not without its challenges. Quantum systems are highly sensitive to their environment, and any interaction can cause loss and decoherence, degrading the squeezed state. Precision in nonlinear processes, thermal noise, phase stability, detection efficiency, technical limitations, and scalability are all hurdles that researchers must overcome. Despite these challenges, the potential benefits of quantum squeezing are immense. From enhancing the precision of quantum sensors to improving quantum communication and computing, this technique holds the promise of revolutionizing various fields. Now we'll explore another cornerstone of quantum mechanics, quantum entanglement. Entanglement is a unique phenomenon where two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. This strange and fascinating behavior has profound implications for quantum technology. But how do scientists create entanglement in the lab? Let's dive into some of the most common techniques. This widely used method involves a nonlinear crystal that splits a single high-energy photon into two lower-energy photons, known as signal and idler photons. These photons are entangled in properties such as polarization or momentum. Here, two photons from a pump beam interact with two photons from a probe beam in a nonlinear medium like an optical fiber. This interaction generates pairs of entangled photons. 3. Engineered semiconductor nanostructures known as quantum dots can emit pairs of entangled photons when excited. This process is called the B-exciton cascade. By trapping ions or atoms in electromagnetic fields and using laser pulses to manipulate their quantum states, scientists can create entanglement. This method is often employed in quantum computing and information processing. 5. In superconducting circuits, entanglement is created by coupling qubits through microwave photons, a technique crucial for building quantum processors and computers. In cavity QED, atoms or ions placed inside an optical cavity interact with the cavity's electromagnetic field, producing entangled states. Entanglement plays a crucial role in the behavior and utility of squeeze states in quantum mechanics. Here's how. 1. Entanglement can enhance the degree of squeezing. When two or more quantum systems are entangled, the correlations between their properties can be exploited to achieve greater noise reduction in one of the systems. This is particularly useful in applications like quantum metrology, where high precision is required. 2. In quantum information processing, entangled squeezed states perform tasks impossible with classical systems. For example, in quantum teleportation, entangled squeezed states transfer quantum information between distant locations with high fidelity. 3. Entangled squeezed states improve the security of quantum cryptographic protocols. The correlations between entangled particles detect eavesdropping attempts, ensuring secure communication channels. Entangled squeeze states are employed in quantum sensing and metrology to achieve measurements with precision beyond the standard quantum limit. For instance, in gravitational wave detectors like LIGO, entangled squeeze states help reduce noise and improve measurement sensitivity. 5. In quantum computing, entangled squeezed states are used in error correction protocols. The entanglement helps detect and correct errors during quantum computations, improving the reliability and efficiency of quantum computers. In the LIGO experiment, which detects gravitational waves, squeeze states of light are used to reduce quantum noise. By entangling these squeeze states, LIGO achieves even greater noise reduction, enhancing its ability to detect the incredibly faint signals from distant cosmic events. Entanglement amplifies the benefits of squeezing by leveraging the strong correlations between quantum systems, making it a powerful tool in various quantum technologies.